Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. In the last lecture, I was discussing about the analysis of coal, and I had discussed about the proximate analysis, which is done to calculate the different parameters which are present in the coal, like moisture, like volatile matter, ash content and percentage of fixed carbon. Today I will be discussing about the ultimate analysis of coal. Now this ultimate analysis, it is also the elemental analysis, and it is called as the qualitative analysis of coal. Now with this analysis we can determine the percentages of carbon, hydrogen, nitrogen, sulphur and oxygen which are present in the coal. Now coming first to the calculation for percentages of carbon and hydrogen. For calculating carbon and hydrogen, we take about 1 to 2 gram of weighed coal sample. It is taken or it is burnt in a current of oxygen in a combustion apparatus, where the carbon and hydrogen, they are converted into CO2 and H2O respectively. And these gaseous products of combustion, they are absorbed over KOH. CO2 is absorbed over KOH, while H2O is absorbed over calcium chloride tubes which contain their known weights. And when they are going to absorb CO2 and moisture in the respective tubes, the weight of the tubes are going to increase, and the increase in weights of these are then determined. Therefore, the equation that takes place, the carbon, it burns in the presence of oxygen to form CO2, and this CO2 is absorbed by the KOH which is present in the tube to form K2CO3 plus H2O. Similarly, hydrogen on combustion produces H2O, and the calcium chloride tubes absorbs water to form hydrated calcium chloride. And the percentage of carbon can be calculated as increase in the weight of KOH tube. On absorption the weight will increase, so increase in the weight of KOH tube divided by the weight of coal sample taken. What was the weight of the coal sample in which we are determining the percentages of these different elements, multiplied by 12 by 44. According to this equation, 12 grams of carbon combines with oxygen to form 44 grams of CO2. So multiplied by 12 upon 44 into 100. Similarly, percentage of hydrogen is given as increase in the weight of calcium chloride tube divided by the weight of coal sample taken, and according to this equation, 2 grams of hydrogen produces 18 grams of water, so multiplied by 2 divided by 8 into 100. This is the representation how we calculate the percentage of carbon and hydrogen. This is the pure dry oxygen which is running inside the combustion tube, and these are the two different U tubes where one contains anhydrous calcium chloride and the another contains KOH solution. So water, moisture get absorbed here, whereas CO2 get absorbed here, and the excess O2, it moves out from the system. Now the second method is the determination of percentage of nitrogen which is present in the coal by Geldas method. Now what we do in the Geldas method, we take around 1 gram of the weighed powder coal, and this powdered coal, it is heated in concentrated sulfuric acid along with K2SO4 and CuSO4 as catalyst, and the method is known as Geldas method because it is conducted in a long neck flask known as Geldas flask. And after we treat it with concentrated H2SO4, we get a clear solution. When we obtain this clear solution, it is treated with excess amount of potassium hydroxide, and when we treat it with KOH, we get liberated ammonia is liberated, and this liberated ammonia, it is distilled over and it is absorbed in a known volume of standard acid solution, and this acid solution is of 0.1 normal sulfuric acid. And now the unused acid, because we are using excess amount of acid here, so the unused acid, it is then determined by the back titration with standard NaOH solution, which is 0.1 normal NaOH solution. We don't know how much ammonia is getting distilled over. So in order to absorb or react complete ammonia with sulfuric acid, we add excess amount of sulfuric acid. So ammonia and sulfuric acid will react to form a product, but excess amount of sulfuric acid will remain in the solution. And this leftover sulfuric acid which is present in the solution, we determine it by titrating it with a known volume of NaOH solution. So we know the initial volume of sulfuric acid, and we know now how much sulfuric acid was left, because N1V1 is equal to N2V2. Since the normality of sulfuric acid and NaOH is same, therefore the volume are also going to be same. So from this titration and this equation N1V1 is equal to N2V2, we can calculate how much sulfuric acid is left. So from total sulfuric acid, if I minus the sulfuric acid which is left in the reaction mixture, I can calculate the amount of sulfuric acid which was utilized by ammonia. So now from the volume of acid used by ammonia liberated, the percentage of nitrogen in coal, it is calculated as, here nitrogen in the presence of sulfuric acid form ammonium sulphate, which in presence of NaOH from sodium sulphate liberate ammonia and form water. Now this liberated ammonia, it reacts with sulfuric acid again to form ammonium sulphate. This is the setup for determining the percentage of nitrogen in coal. This is the Geldas flask where the reaction is taking place, and this is the distillation assembly where we are going to do the different reaction where distilled ammonia is going to get reacted with sulfuric acid, and the leftover sulfuric acid, it is again getting titrated with NaOH solution. So the percentage of nitrogen in coal, it is calculated as the volume of the acid multiplied by normality of the acid, volume of the acid consumed by ammonia, and this can be calculated as total volume minus the volume which is consumed by NaOH divided by the weight of coal taken multiplied by 1.4, or it is multiplied by 14 multiplied by 100 by 1000 in terms of milli equivalents, and on calculation we get 1.4. Next is the determination of sulphur, and now this sulphur, it is we determine it from the washings obtained from a known mass of coal which is used in the bomb calorimeter for the determination of calorific value. So for determining the presence of sulphur, the percentage of sulphur in coal, the sulphur, it is converted into its sulphate, and the sulphate which are being formed, these washings are then treated with barium chloride, and when we treat the washings containing sulphate with barium chloride, barium sulphate is precipitate. It is precipitated, a precipitate of BaSO4 is formed. So now the precipitate is going to be filtered, it is going to be washed and then heated to a constant weight, and the percentage of sulphur we can determine by weight of barium sulphate formed, because all the sulphate will react with barium chloride to form the precipitate of barium sulphate. So the weight of barium sulphate obtained divided by the total weight of coal which we had taken in the bomb calorimeter multiplied by 32, because in barium sulphate it contains only one sulphur and the molecular weight of barium sulphate is 233 multiplied by 100. So in this manner we can calculate the percentage of sulphur. Next, for calculating the ash, now again the ash is calculated in a similar manner as we had determined in the proximate analysis. Now the residual coal which is taken in the crucible and then heated without a lid in the muffle furnace at around 700 to plus minus 50 degrees centigrade for half an hour. Now the crucible is taken out, it is cooled first in air and then in desiccator, and then it is weighed. And this heating, cooling and weighing, it is repeated till we obtain a constant weight. And now this residue which we have obtained, it is reported as ash on percentage basis. And we can calculate the percentage of ash as weight of ash left divided by the weight of coal taken multiplied by 100. Next is the determination of oxygen, percentage of oxygen. So this percentage of oxygen is just determined indirectly by deducting the percentage of carbon, hydrogen, nitrogen and sulphur from 100. So percentage of oxygen is equal to 100 minus percentage of CHSN plus ash. If we minus all these from 100, we will get the percentage of oxygen which is present in the coal. Now, coming to the significance of ultimate analysis. First, carbon and hydrogen. Greater is the percentage of carbon and hydrogen, better is the coal in quality and calorific value. But hydrogen is mostly associated with the volatile matter. Therefore, it affects the use to which the coal is put. Next, percentage of nitrogen. Now, this nitrogen, it has no calorific value and hence its presence in coal is undesirable. So, a very good quality coal should have minimum amount of nitrogen content. Next is the sulphur. Sulphur undergoes combustion reaction. Sulphur in the presence of oxygen forms SO2 and SO3. But this sulphur accounts for the heating value, yet it produces harmful products like acids, SO2, SO3, which have harmful effects of corroding the equipments, and they also cause atmospheric pollution because they ultimately lead to the formation of sulfuric acid. Sulphur is usually present to the extent of 0.5 to 0.3%. And it is derived from the ores like iron, pyrite, gypsum, etc. mines along with the coal. Now, the presence of sulphur is highly undesirable in coal, which is used to be making coke for iron industry, since it is transferred to the iron metal and badly affects the quality and properties of steel. And oxides of sulphur pollute the environment and they lead to corrosion. So, the more quantity of sulphur is again not desirable in the case of good quality coal. Next is the ash. Now, ash is useless and again it is non-combustible matter and it reduces the calorific value of coal. Along with that, ash also causes the hindrance to the flow of air and thereby lowering the temperature. So, lower is the ash content in coal, better is the quality of the coal. And the presence of ash, it also increases the transportation cost, the handling and the storage cost. And the presence of ash, it also causes the early wear and tear of the furnace walls and burning of the apparatus and the feeding mechanism. And again, ash disposal is also a problem. So, we have to give an input of the cost for the ash disposal. Next is the presence of oxygen. Now, oxygen content, it decreases the calorific value of the coal. Why? High oxygen content coals are characterized by high inherent moisture. Generally, the oxygen which is present in coal, it is present in the compounded form. Hydrogen, it forms H2O with hydrogen. So, it is characterized by the high inherent moisture, low calorific value and low coking power. And this oxygen, it is in a combined form with hydrogen and coal, and thus hydrogen available for combustion is lesser than the actual one. So, more is the percentage of oxygen, more oxygen will combine with hydrogen and lesser oxygen will be available for the combustion process. An increase in 1% oxygen content decreases the calorific value by about 1.7%. Therefore, oxygen is again undesirable for a good quality coal, and a better coal should have low percentage of oxygen. Next, coming to the combustion and the calculation of air. We all know that the combustion is an exothermic process, and all the fuels, they undergo combustion. These fuels, in the presence of oxygen, they form products, combustion products, and they liberate heat, useful heat in the process. Now here you can see I have written some equations. These are the combustion reactions. Carbon, it reacts with oxygen to form carbon dioxide. So here you can see 12 grams of carbon are reacting with 32 grams of oxygen to form CO2. If x grams of carbon is present, then it will react x into 32 by 12. Similarly, hydrogen reacts with half of O2. That means 2 grams of hydrogen are reacting with 16 grams of oxygen. And if B grams are present, then B will react with B into 16 by 2. Similarly, I have calculated how much of the elements which are present, which undergo combustion, they are going to be present, and how much oxygen they are going to require. And from these different equations, I can sum up the total oxygen requirement or the total requirement of the air which is required for the complete combustion of any fuel. And because some fuels, they also contain oxygen, so the minimum oxygen required from the environment for the combustion process will be, we are calculating the theoretical from these values, so it will be equal to the theoretical oxygen required, and because oxygen is also present in fuels, we are going to minus that oxygen which is present in the fuels. So our requirement of oxygen will be equal to the oxygen which is coming from the different calculations which is required, and minus the oxygen which is already present in the fuels. Now, the total amount of hydrogen is either present in the combined form or free form, and only free form of hydrogen, it is available for combustion. So it is H minus O by 8. I have already discussed in the calorific value part how we calculate it. And if the fuel contains nitrogen, ash and CO2, they are non-combustible. We are not going to count the oxygen requirement for all these three because they don't undergo the process of combustion. Now, in air, oxygen is present 21% by volume and 23% by mass. So, the volume of air required, these are the oxygen calculation, but we are not supplying oxygen. We are doing the combustion process in the presence of air, and air contains 21% by volume of oxygen and 23% by weight of oxygen. So, the volume of air which is going to be required to give this much amount of oxygen, it is going to be equal to oxygen required into 100 by 21 liters of air will be required. So, the weight of air actually supplied per meter cube of the gas, it is equal to the volume of the air into 28.97 divided by 22.4 grams, where 28.97 gram per mole is taken as the molar mass of air. So, from this conversion factor, I can convert gram into liters and liters into gram. And the minimum oxygen which is required by weight, it is equal to the oxygen required, which we are going to do with different calculations, multiplied by 100 by 23. And the excess amount of air, if it is given in the numerical that the fuel requires excess air, then the excess amount of air required, it is given as Y, where Y is the percentage of excess air required. Y plus 100 divided by 100. So, these are the different things, different parameters which we have to remember for the calculation of air. Now, I have taken one example. Calculate the weight and volume of air required for combustion of 3 kg of carbon. Now, we have already seen that the carbon, it undergoes combustion with oxygen to form CO2. So, 12 grams of carbon reacts with 32 grams of oxygen. Therefore, the weight of oxygen required for the combustion of 12 grams of carbon is 32 grams. And weight of oxygen required for the combustion of 3 kg. 12 grams require 32 grams and 3 kg will require 3 multiplied by 32 by 12. So, the 3 kg will require 8 kgs. 3 kg of carbon will require 8 kgs of oxygen, and 8 kgs of oxygen will be supplied by how much air? So, weight of air contains 23% oxygen required. So, 8 kgs of oxygen will be supplied by 100 by 23 into 8, that is equal to 34.78 kgs. And as per Avogadro's law, now 32 grams of oxygen, it occupies 22.4 liters at NTP. Not only 32 grams, every gas at NTP occupies 22.4 liters. So, 8 into 1000 grams of oxygen will occupy how much volume? It is going to occupy 22.4 divided by 32 into 8 into 1000, that is 5600 liters. And the volume of air which contains 21% oxygen required for the combustion, this is in terms of the volume, it will be equal to 100 by 21 multiplied by 5600, which is equal to 26.67 meter cube. So, this is the volume of the air required, and in terms of weight, this is the weight of the air which is required. Here are some numericals. This is the Geldas method which I had discussed, where we can calculate the calorific value on the basis of percentages of carbon, oxygen, hydrogen, sulphur which are present in the coal sample. This numerical is on the basis of, again, Geldas formula. Now, this numerical is based on the basis of bomb calorimeter, where we have given the different percentages, but we have given the weight of the coal, weight of the water which has been taken, water equivalent, T2 minus T1 rise in temperature is given, fuse wire correction, acid correction, cotton thread, cooling, all corrections are given, and putting these values here, where capital W is 570, small w is 2200, T2 minus T1 is 3.3, cooling correction is 0.047, acid different corrections divided by the weight of coal, and the weight of coal is 1.029. So, these are the answers which I had calculated, and this numerical is for the air requirement. When the fuel contains different percentages of carbon, hydrogen, oxygen, sulphur, water, where moisture, it will not undergo combustion, nitrogen and ash will also not undergo combustion. So, we are going to do the different calculations for these and then add up how much oxygen is required, and finally, what is going to be the weight of air required. Thank you.